Good morning. I am Professor Abhijit Mondal, a professor in radiological physics, and I am working in the Department of Radiation Oncology, Institute of Medical Sciences, Banaras Hindu University, Varanasi. In the radiation oncology, if we say in one liner that we treat cancer patient by using radiation, but this one liner involve a huge amount of physics, mathematical calculations, technological informations, and regulatory and safety and protection information to accomplish or to execute the radiation treatment of cancer patients. In radiation oncology, we have various kind of personals. If we define what are the three aim of radiation oncology, means the man, the machine, and the moment of radiation oncology. We have various type of, in man we have various type of professionals such as radiation oncology, radiation oncologist, they are clinician, and they have different type of degree, that is MD radiotherapy and DNB radiotherapy, sometimes the diploma in radiotherapy means DMRT. All these type of clinicians, they work as a radiation oncologist. They define the cancer staging and all the clinical aspects for radiation oncology management of cancer patients. And we have in our department, we have radiological physicist, sometimes they are known as medical physicist, who plan the treatment methods or treatment procedures, what are the amount of radiation and how this treatment plan is to be executed for the treatment of cancer patients. And we have a other type of professionals, they are radiotherapy technologists. So they actually execute the planned treatment in the therapeutic machine. So they treat the cancer patients directly. And in this radiation oncology, as I have mentioned in one liner, that we treat the cancer patients or we treat the cancer by using application of radiations. Now in terms of radiations, any kind of propagation of energy is termed as radiation, but here we use the ionizing radiations. Means these radiations having the capability to ionize the atoms while it passes through the material medium. Now the radiation is hazardous to the, or it is having the lethality towards the cells of human body. So by using their lethality effect of cells, we use to treat the cancer, the target volume where the cancer cells. But you see, there is some amount is cancer cell, or we define as a target volume, and the rest of the part is actually the normal tissue. So if we irradiate this normal tissue, this is also normal cells, they are also affected, and there will be also complications of this treatment. So we have to treat, or we have to focus our treatment by giving the maximum dose to the target volume as minimum as possible dose to the normal structures or normal cells. So this is the challenge in radiation oncology, and to execute this challenge we have used various kind of equipment, various kind of therapeutic equipment, various kind of simulation equipment, imaging equipment, and we have various kind of measurement equipment and calibration equipment, and we have also verification equipment to execute this precise type of and sophisticated type of treatment for cancer patient, so that target volume is treated properly and sparing the normal cells. And this is all about in this radiation oncology physics course. We learned all these 40 following lectures, and today I am going to deliver the lecture number 1, where we will discuss the basic atomic and nuclear physics. This is, I hope that all of you must gone through this topic from your academic program, in your academic curriculum from 6 onwards, and we will learn step by step, and some people may get a very in-depth knowledge in this topic, basic atomic and nuclear physics. But here we will discuss a very basics, and this is a quick recap of your earlier knowledge. So in this basic atomic and nuclear physics, we know that something which occupies space and having finite mass and are composed of elements are known as matter, and elements are distinguishable from others, from one element to other element are distinguishable by the terms of their properties. One is physical properties and another is chemical properties. We know each matter having some, if a steel is one type of matter, wood is one type of matter, and air is also a matter, and water is also a matter. So they have different type of physical properties and they have different type of chemical properties. Now atom, this is the basic component of matter and smallest and indivisible particles which maintains the properties of the element. So this is the basic, fundamental and smallest indivisible particle which maintains the properties of the element. So we call it this basic component, this basic particle is known as matter. Now matter is composed by various kind of particles. There is a inner shell, and this is heavy. There is a inner part and inner core, this is known as nucleus, and this nucleus contains the protons, this is positively charged, and we have neutrons, they have no charge. So ultimately the nucleus is a positively charged, a combination of protons, some protons and some neutrons, and outside the nucleus there is electron. There is electron and their positions and speeds are defined in many models of atomic models. Sometimes they called as particles, sometimes they called as waves, sometimes they called as cloud of electron. So just we consider here as particle. They are negatively charged. So atom is actually a electrically neutral, because the number of protons is equal to the number of electron outside the nucleus. So it is electrically neutral, and protons are heavy, their mass is higher, much higher, they are almost equal to the neutrons, and electron is much lighter particles which orbits around the nucleus. Now this is the atomic notation we used in our physics or chemistry subjects. So we know that atom is defined as Z, X, A, where X is the chemical symbol of the element and Z is the atomic number. This is the number of protons in the nucleus, and A is the mass number. This is the total number of nucleons present in the nucleus. So Z is the atomic number, this is number of protons in the nucleus, and if atom is electrically neutral, that it is also equal to the number of electron in the orbits. So this is, they are equal number of protons and equal number of electrons, and A is the mass number, where mass number means total number of nucleus present in the nucleus. So in example, if we see one example, one or two example, one is 1H1 means this is H, this is the chemical symbol of hydrogen, H is the chemical symbol of hydrogen element, and 1 means the nucleus of hydrogen having one proton, and in hydrogen atom there is no neutrons, and 1 is the mass number. So the total number of neutrons nucleons here is 1. So 1H1. So number of electron and number of protons are equal here, and the mass number is 1 and the atomic number is also 1. Now if we see the helium atom, we have 2He4, H is the element, chemical symbol of the element, and 2 is the number of protons and 4 is the mass number. So in this helium atom we have proton 2 number, neutron 2 number. So total number of nucleons A is equal to 4. So here it is 4, and we have number of electrons is also, if it is electrically neutral, then it is in number is 2. We will discuss some important definition regarding our radiation oncology. We will use some various kinds of radioisotopes. So iso means same. If two or more thing having same, so we define them as a iso. And here is isotope, the atoms having nucleus same atomic number and different mass number. They are known as different mass number but same atomic number. They are known as isotopes. 1H1 and 1H2, they are isotopes. Isobars is atoms having same different mass number but different atomic number, same mass number but different atomic number, they are known as isobars. And we have isotones, atoms having same neutron number, sorry it is written here, same neutron number but different atomic number, they are known as isotones. If we consider here, there is C14, 6 and 8O16, we have a proton number here is 6 and proton number here is 8, but the neutron number is 8 and here also neutron number is 8. So neutron number is same in C6, C14 and 8O16. So they are isotones. Similarly, we have isomers, but here we have same atomic and mass number but they have different energy levels. So this is 28 nickel 60 and we have 2860 M. M is placed here. This is the metastable state, or you can call it as excited state. So when the cobalt 60 28 irradiated one beta particles and gamma emissions, we will have the nickel first it comes to the metastable state and again emission of gamma photons, it comes down to the stable of nickel state. So here the all are same atomic number and mass number, but only difference is M60 M means this is different energy level, this is metastable state. Now I will discuss some very basic atomic models which are for completeness of our lecture, because nowadays various advanced atomic model have been proposed to define all the phenomenon related to the physics and chemistry, but these are basic and old atomic model which are defined, which are proposed by then scientists such as J.J. Thomson, such as Rutherford and Bose. We will discuss only 3 models. They are basic, very fundamental and basic models to understand the radiation oncology physics. So Thomson was first defined the atomic model, and while he used he was studying cathode ray to produce and stream of negatively charged particle, and they are named as electron, and he proposed a model that is known as palm pudding model. That is known as palm pudding model. And he thought and he proposed that atoms might be made up of combination of particles. They are positively charged particles and they are negatively charged particles. They are like palm pudding type of structures where they are placed almost uniformly. These positively and negatively charged particles are distributed uniformly. But Geiger and Marsden in 1909 they conducted an experiment and they considered the alpha particles emitted from radium C, and they are targeting this alpha particle radiation beam towards a gold foil, and this gold foil thickness is very low and 0.0004 centimeter, and they observed that there is scattering of the alpha particles, because alpha particles are heavy particles, they are having the 2He4, so they are considered as a heavy particles, and even these heavy particles are also scattered. So they observed that more than 99% of the particle scattered at an angle less than 3 degree of scattering angle. These are the scattering which they observed. They are very 99% of particles they observed and scattering of angle less than 3 degree. But 1 in 10 to the power 4 alpha particle means 1 divided by 1,000,010 to the power 4. This is the percentage, or this is the fraction of alpha particles they observed. They are scattered at an angle more than 90 degree. Now, how this heavy charged particle is scattered in such a high angle? So, after seeing their result, Rutherford proposed one model, and he thought there must be a very dense central part, and after that he defined this as a nucleus, and outside this nucleus there must be orbiting electrons, and this is the Rutherford model he proposed, where positive charged are placed within the nucleus and negatively charged electrons they are orbiting around the nucleus. This is the Rutherford model. Now, what happened that if a charged particle revolve around the nucleus in a circular path, this charged particle in motion would undergo the acceleration, and it also cause the radiation emissions, means a decrease of energy, and ultimately this electron is spiraling and accelerating and may collide within the nucleus. So, there is a severe drawback in the Rutherford model, that is the stability of the atom, and this is not explained properly, and this is not explained at all in the Rutherford model, and so stability is the main problem and drawback of Rutherford models, where spiraling and accelerating electron collide goes to the nucleus like this. It is coming to the nucleus, and the electron and the atomic existence is in the stake and in the question. Now, Bohr has given and eliminated this problem, and he thought and he proposed that electrons can rotate around the nucleus in fixed orbit. In the fixed orbit, their rotation, there will be no emission of energy, and there will be no emission or emission of energy. So, they have the fixed orbit. Their size and energy are fixed, means they are fixed orbit. Now, if there is no emission and of energy, now energy of the orbit is related to the size, means bigger the size, bigger the higher the energy, and the radiation emitted or absorbed when the electrons move from one cell to other cell. There is a, if there is a emission, then it is coming down to the lower cell, and if there is a absorption of energy, it may go to the higher state, that is known as the excitation. The K cell is the innermost electron orbit in the atom, and the next cell are L, M and O, and the maximum number it can hold by the by one cell is 2n square, where n is the orbit number. Now, if we put here is for K cell, that is n is 1 and the electron number is 1. So, K cell there will be only 2 electrons. The K cell there will be only 2 electron. Now, if we increase the orbital number, it will, the number of maximum electron will be increased as per this 2n square formula. Now, one important definition is atomic mass unit. It will be used in later for many times. Now, what is atomic mass unit? Atomic mass unit is the, we can sometime call it as AMU, and it is the 1/12 of mass of the carbon atom. Here we have a carbon atom, and where there will be 6 protons and there will be 6 neutron, and if we convert this atomic mass in the energy, we know that E is equal to mc square. There is a mass to energy conversion formula, and by using this formula, the 1 AMU is 931 mega electron volt is the energy is produced if we convert this 1 AMU rest mass. This is atomic mass unit. So, this is a important definition for in atomic physics. Now, by this energy mass energy equivalence formula, E is equal to mc square, the energy equivalent of an electron rest mass is 0.511 MeV, and 1 MU is, we have already defined, that's 9.31.5 MeV. So, electron is very small mass and is very negligible mass in the of the electron. Now, particle wise, electron having charge of minus 1.602 10 to the power 19 coulomb, minus 19 coulomb, and rest mass is equal to 0.511 MeV, and proton having the same charge, where plus positive 1.602 10 to the power 19 coulomb, and the rest mass energy is 938.28, and the neutron, they have no charge. So, the charge amount is null, and the rest mass energy is 939.57 mega electron volt. Now, we can see that the charge of electron and charge of proton are same, but mass, rest mass of electron and rest mass of proton are very different, and proton is much heavier than electron, but proton and neutron, they are almost equivalent in mass. So, they are almost equal, 9.3828 MeV and 939.57 MeV of the rest mass energy for protons and neutrons. Now, this is the nuclear energy level. We know that as per electrons there are energy levels, nucleons means protons and neutrons, they are also arranged in discrete energy levels. Here, this is the very commonly used decay scheme of cobalt 27 cobalt 60 with a half life of 5.26 years. First, it emit the 99.88% of beta emission of 0.31 MeV, and it is the nickel 2860 excited state, and again emit 1.17 mega electron volt of gamma photons, and it comes down to this 28 nickel 60. It is also again another excited state, and after emission of 1.33 mega electron volt of gamma photon, it comes to the stable nickel stable nickel form, and these all are actually the iso, they are known as isomers. They are differ in their energy levels, which I have already discussed in earlier slide. So, nucleons, here we see that nucleons are also arranged in discrete energy level status or states of the nucleus. Now there is one question, that how these positively charged protons and uncharged neutrons, they are referred as nucleons, are combined and stay together in a very small volume, because there is a nuclear force is present to to bind all these positively charged protons. This nuclear force is very strong force, and it is very short range force. Short range means they are active only very few femtometer distance, and you know that 1 femtometer is equal to 10 to the power minus 15 meter. Now this strong, from where this strong force is coming, from where this strong force is coming, they are coming from the mass defect. Mass defect, if we divide the each component of any atom, and if we of any nucleus, and we combined again the nucleus, the mass of part by part nucleons is higher than the combined nucleus. So this is the mass defect we getting, and this mass defect is converted to the energy and acting as a nuclear force, and this is a as I have mentioned, that this is a strong force, and this strong force is short range and active only distance of few femtometers, and 1 femtometer is 10 to the power minus 15. And this is all from today's class. Thank you.